Thank you. So yeah, this talks about scaling with Django. So just, oops, hold on, something's wrong. There, okay. So I noticed upstairs when people were looking at slides yesterday that there were a few issues reading the slides. And there is code on these slides, so if you have like a tablet, a laptop, iPhone, whatever, you can jump here real quick and pull up the slides. Give you a few seconds. If you can't read the link, oh, you have to get it from a friend. Anyway, I'm going to move on.
Go back.
Oh, jeez. Okay, I got to go. Speed up time here. So I work at Wave Accounting. I'm director of platform there. So this talk is actually going to be using my experiences scaling at Wave Accounting. So it's just kind of is a caveat. You're going to see a mix of some general examples, and I'm actually going to pull in some examples from the stuff we worked on, because it was just easier to pull things in right from the code base. So we'll jump in real quick. Generally, we have two reasons why we would look to scale a database. The first is we need to write faster. A single database can only do so many I/O operations. So as you start to saturate your I/O, you need to scale that out. The other main reason is you have a lot of data. And specifically, there's a limit to how much data you can keep kind of hot in memory. A killer is if you can't keep your indexes in memory. That's a killer, right? It's a killer, sorry. So I'm going to talk quickly about three strategies you can use with database scalability. I'm going to fly over a few of them, and then we'll kind of stop with the more interesting ones. The first strategy, which you should always do, is just scale up. Really, really simple. You want to throw money at the problem. You want to buy faster processors, buy more processors, buy faster hard drives, go SSD, buy more RAM. And if you can, if this is all the scaling you need to do, then actually you're in a pretty good position, because everything after this introduces more and more complexity into your system. The next kind of strategy is feature partitioning. Some people call this vertical partitioning or vertical sharding. The idea is that you want to route specific types of data to specific databases. So in this case here, we have a default database with, say, your users, maybe some general profile information. Then we're going to move, say, accounting data to one separate database, and then transactions to a different database. A tool that we found that's really useful when going to a multi-database setup is using DJ database URL, written by Kenneth Reitz. And they actually use that at Heroku, or it was introduced actually a couple of months ago at Heroku. So it allows you to define your databases in terms of URIs. So when you start having tons and tons of databases, this is a lot cleaner than having those really verbose database dictionaries. So when you're looking at feature partitioning, I know it's very small, so if you have it on your laptops or whatever, you can read a little bit better. We chose to do something. We chose to build something called an app-based router, and the idea there is that we're going to take all the data from a particular Django app and route it to a specified database. So you can take this app-based router, extend it, and set a class variable for the app name and the DB name. We also built another one, which I don't have on slides, which allows you to specify a database name and a list of apps that should actually to go to that same database. No need to squint. We're going to go over the actual pieces of the router here. For reading and writing to a database, in our case, it's actually the same method. So what we're going to do is we're going to check the model classes meta argument, and we're going to check the app label on there and check if that matches our app label that we've defined for our app-based router. If it does, we're going to return the database name that we want to write to, and that's one of those database aliases that you set up in your settings py file. Same thing happens for your writes. The next method you define in a router is your allow relation, and this takes two model instances and lets you kind of do some comparisons on it. If the two objects exist in the same app, then we're going to allow you to set up foreign key relations. If only one of the objects is in the app, we don't allow foreign key relations. And the reason for that is you can't actually have foreign keys across separate databases, or at least not with any of the databases that Django currently supports out of the box. And if you have two objects and none of them are within the app that you specified, you're going to return none, which basically says I have no opinion, and let some other database router make a decision further down the line. The next method in your router is allow syncDB, and this is going to signal Django to sync the DB or sync the DB for a given model and for a given database. So if the database is equal to the database that you set in your router, and your model app label is the same as the app label that you specified in your router, then we're going to, in this case, obviously return true and tell the router to allow a syncDB to happen. Otherwise, we're going to return none, which is, again, I have no opinion. There's a little bit of interesting piece up at the top, and this is with South. So I'm not sure. I assume that most people are using South when they kind of write their database applications. It's what I use, and so I'm familiar with this. You need to sync South on every single database you have. You need to have your South migration history table on every single database. So we just hard code in if the app label's South, we're always going to sync that. So now once we go to a multi-database application, it's not free. We actually lose quite a bit of things that Django gives us. The first thing, as I mentioned before, is we lose our foreign keys. You can't take your user model and reference that in, say, a transactions model or a post model or something like that. So instead, what you're doing is you're kind of maintaining your foreign key in your application. Your database actually just has an integer, and then you're gonna maintain that relationship in your application. We're going to potentially lose the ability to use select related, so you can't actually join tables that are on separate databases. And if you were like me and you've been waiting for Django 1.4 to launch, you can use prefetch related, and you don't actually have to maintain your caches internally. Well, you can't use that anymore, and you're going to have to go back to the old strategies you were using. And if you have models over multiple databases, you can't actually cascade your deletes because you actually don't have real foreign keys. You have just references. So if you are happy with losing all that, you can move on to the next step, and that is scaling horizontally. And generally, we're going to be talking about sharding your data. And for people who aren't familiar, what this means is you're basically running the same schema on multiple databases. So the first thing we're going to do is we're going to start by picking a sharding key. And this is probably your most important decision when you decide you're going to start sharding your data. And you can actually shard on multiple sharding keys and multiple partition keys. The first thing that we found that was helpful was analyzing our data models, and more specifically, analyzing the relationships between our models. We found it really useful to map out an ERD and actually get a visual sense of kind of how our data looks. So if you have an ERD that looks like kind of like this, this is actually like a really easy database schema for you to shard and to scale. So we can see, maybe it was apparent, maybe it isn't apparent, but this key in the middle there actually is the key that we want to be using to shard an ERD like this. And we know we have a good sharding key. Sorry. There's two reasons why we have a good sharding key. One is that it's usually a primary identifier for one of the major models in your application. The other one is that it also gives you the most number of subgraphs when you shard on that. So if you remember back to that slide, we actually had 3 different subgraphs, which was maximizing the number of subgraphs we had. Maybe you're not so lucky and you have data that's extremely relational, everything's tied together, you can't pull anything out. There is no real cut and dry way to shard this. It's going to come down to analyzing what your application's doing, how people access your applications, and this is kind of like one of those non-answers, like it depends. But it really, this is really going to come down to the specifics of your application. So if you've picked a sharding key, how do you know if you have a bad sharding key? This is the easiest way to find out. If you have to query all of your databases to find a particular piece of information, so if I, say, had a blog engine and I'm sharding a user's blog posts over n databases, and I have to query n databases to get all the blog posts for a user, blog post isn't a very good key to be sharding on. So yeah, if you have to query all the shards, that's a good idea or gives you a good idea that you actually have a poor sharding key. Also, if your data is saved disproportionately across all the shards, if you've got 10 shards and you're piling up all your data in the first 1 or 2 shards, then probably the key you have isn't working out for you. Once you've picked your key, we need to specify our databases, and there's a little bit of a tweak that we make here. We've extended the DJ database URL package that I talked about before. And we added some stuff so that we can actually add extra options to our databases dictionary. So now you can see that our database dictionary gets defined like this. And so you can actually have tons and tons of databases defined. The interesting thing, though, is we added this arbitrary shard group. And that allows us to, if you have multiple shards, multiple systems of sharding, you can identify an entire set of databases and apply operations to them. And this is really useful because we need to extend South again. South has support for multi-DB, but it's very limited. And there's a few things that you need to do. The biggest thing is you need to fake your migrations on your default database. And this is really important for your development process. You do this so that we guarantee that the sharded data doesn't exist on our default database. The reason we want that to happen is if myself as a developer or one of my coworkers accidentally tries to write sharded data to a non-sharded database, we want it to throw an error and to inform the developer that they've made a mistake. So we basically fake that migration so that we don't create the tables, but South considers those tables to be there. The next thing is that as you make migrations, you need to run those migrations on every single shard. So what we've done is we've taken these 3 points and we've put them together into a custom management command that we can run that will create our default database and then take those sharding keys and iterate through every database with the same sharding key and apply the same migration operation to it. We actually extended South so you can do things like, in our case, it's Python manage wave migrate -- list, and it'll give you all your information for the default database. You can go -- list shard group equals your shard group, and you can actually get output of all the you can get the South output for all of your different shards. So now that we have now that we're using sharding, the router actually changes a little bit. We have a DB for read method that's a little bit different. We have to now start using the instance if it's passed. Right now, an instance variable may or may not be passed on the hints keyword args. So we want to actually get the instance off if we can. And if we have an instance, we're actually going to ask the instance to determine what where its shard is or where it should be sharding its data. Otherwise, we're going to return none. Basically, we have no opinion. The interesting there is when we return none, that forces now the user to make a decision in the application about where they write their data. There is no more automatic routing of data. So, like I said, we're going to delegate the shard selection to the instance. The reason we did this is we can now put a getShard method on every model that we have that's sharded, and then each model has the responsibility of determining where it needs to store its data, as opposed to trying to put that implementation details in the actual router. So the instance getShard looks like something like this. First things first, if we already have the state, so if we've pulled in an instance from the database, we're going to have the state stored in the database. So we're going to use that if we have it. The next thing is if we don't have an instance, or if we don't have the state, we're going to ask we're going to call some method that will tell us for this particular model where should I be putting this data. For the allow relation, we're actually not going to implement it because we don't want to be able to. If you have sharded data, you don't want to take one foreign key from one shard and try and apply it, or try and have a relationship with something from a different shard. So, and then allow sync to be same thing as before. We're going to add South in, and then a little bit of a difference here is we're going to check whether the database starts with, so that we can, if we have a uniform naming schema, we can actually sync for a whole number of databases. So now when we want to read from a shard, you basically have to have some sort of method that's going to tell you what shard to use. Presumably, you're using your sharding key to determine that. And then you're going to take your model and you're going to pass in a using. You're going to pass in the shard to a using method on your query or your query set, and it will tell it, go get this, go apply this at this particular database. When you write to a shard, you're doing it to 3 different ways. Again, you're getting your shard. You're either specifying it on your query set, or you are specifying it on a create on your query set, or you're actually going to pass it into your save method. The next issue that we had to deal with came with balancing shards. And we decided that balancing is actually really hard, especially for the type of data we had. It's very relational. So we decided actually to ignore balancing our data altogether. And instead, we actually are going to run many logical shards on a physical node. The benefit here, there's a few benefits. The first benefit is that if we want to migrate data from shard to shard, you can use MySQL replication or anything like that to basically copy data over. And it becomes more of a DBA and a DevOps task rather than a developer task. The second thing is that when you have tons and tons of data, there's a reason you're sharding. Well, if you wanted to index a column on a 100 gig database or a terabyte database, that's going to take a long time. So adding an index to 100 1 gig shards is a lot faster than an index to 100 gig shard. And you can actually do that in parallel if using Fabric or something like that. The next thing that you have to be aware of is you can no longer rely on your auto increment. You need to start using globally unique IDs. So there's a few ways that we can obtain globally unique IDs. The first one is using the auto increment column on your default database or some other database. The next one is you can write your own ID generator, or you can rely on some sort of external ID generator. Redis, Memcache, they have the increments. You can use Twitter, Snowflake, tons of different things. The first thing we tried was the auto increment column used by Flickr. You can go there and find out more information. The idea there is that we're doing a replace into a particular model, and we're going to rely on the auto increment of that particular model increasing to give us a unique ID every time we request from it. It's kind of crappy, and I do this to kind of get going, but then you want to probably try and use something else in the future. We also defined an external auto ID field, which would, in your pre-save you would actually assign the ID. And you need to add your self-introspection rules. More interesting is the ID generator. So this is something that we've experimented with. You can actually create 64-bit, generally increasing, but not guaranteed to be increasing IDs. You can take your timestamp in the first 41 bits. You can apply a worker ID to your next 11 bits, and then a sequence ID in your next 12 bits. And you can kind of take the last 23 bits and modify them for your needs. So that gives you up to 2,050 unique workers, and then up to 5,000 unique keys per millisecond. So the ID generation looks something like this. We are running out of time, so I'll quickly go over it. The interesting piece is the bit shifting of the timestamp and the worker ID and the sequence. The idea is if you have 2 colliding IDs, what we're going to do is we're going to increment our sequence bit, and that will actually. So the first time we get a collision, we just increment the least significant bit, and it gives us a new unique ID, and we can continue on. So. Right, so in summary, this kind of the first thing you should be dealing with is scale up, feature partition, then shard. If you can stop at any one of these 3 sections, great. Like that, you don't want to have to go the full tilt if you don't have to. The next thing you want to do is make sure you're always picking an efficient key to shard on. I personally don't think that you should try and balance programmatically. Let's use some of the other admin tools and DevOps tools that are available to you. And then you're going to need to start using external IDs or external ID generation somehow. Maybe there's a little bit of time for questions.
Yeah, if anyone has a question, they can step up to the microphone. Maybe just 1 or 2 or.
So a question for you. When you're managing foreign keys between databases that are now vertically partitioned, did you guys write a custom field to handle those kinds of things, or do you just do it manually?
We actually wrote a custom mixin that will actually do, it'll do your get outer, set outer, so that when you try and access a field that is, basically, we create a new field that has an accessor name, an accessor function, and an accessor model.
Sure.
And the idea is that when you try and access a field with the accessor name, we're going to run this accessor function.
Okay.
The default function basically says model.objects.get, passes in the key. The downside there is that if you have a model with, say, 7 of these fields, every time you request one of those fields, you're actually doing a database call, which is really inefficient. So then things like caching and stuff becomes more useful. But once you're dealing with sharding, I would recommend probably using the keys directly as much as you can, and then only actually instantiate the models when you need to.
Okay, thanks.
If I understand well, you shard as much as you can right off the get-go, right? Like as in, you make plenty of shards so that you can manage them between machines, right? Have you considered for the global, like then you don't need the shard after that, right? For the IDs, have you considered offset IDs? Sort of like have the first shard 1, second shard all the even numbers, etc.
Yeah, I mean, I guess that could be a valid way to do that. The problem is when you go to add more shards in the future,
Oh yeah. Well,
now you have to increase your offset.
Hopefully
so.
you have all like a ton of shards right off the get-go. You can set it up.
Yeah, no, actually that could work as well.
Never
So.
have any problems.
Okay, let's thank the speaker.
It was just easier to pull things in right from the code base. So we'll jump in real quick. Generally, we have 2 reasons why we would look to scale a database. The first is we need to write faster. A single database can only do so many I/O operations. So as you start to saturate your I/O, you need to scale that out. The other main reason is you have a lot of data. And specifically, there's a limit to how much data you can keep kind of hot in memory. A killer is if you can't keep your indexes in memory. That's a thank you. So yeah, this talks about scaling with Django. So just, whoops, hold on, something's wrong. There, okay. So I noticed upstairs when people were looking at slides yesterday that there were a few issues reading the slides. And there is code on these slides, so if you have like a tablet, a laptop, iPhone, whatever, you can jump here real quick and pull up the slides. Give you a few seconds. If you can't read the link, because everything after this introduces more and more complexity into your system. The next kind of strategy is feature partitioning. Some people call this vertical partitioning or vertical sharding. The idea is that you want to route specific types of data to specific databases. So in this case here, we have a default database with, say, your users, maybe some general profile information. Then we're going to move, say, accounting data to one separate database and then transactions to a different database. Killer, right? It's a killer, sorry. So I'm going to talk quickly about 3 strategies you can use with database scalability. I'm going to fly over a few of them, and then we'll kind of stop with the more interesting ones. The first strategy, which you should always do, is just scale up. Really, really simple. You want to throw money at the problem. You want to buy faster processors, buy more processors, buy faster hard drives, go SSD, buy more RAM. And if you can, if this is all the scaling you need to do, then actually you're in a pretty good position. Oh, you have to get it from a friend. Anyway, I'm going to move on. Go back. Oh, jeez. Okay, I got to go. Speed up time here. So I work at Wave Accounting. I'm director of platform there. So this talk is actually going to be using my experience of scaling at Wave Accounting. So it's just kind of is a caveat. You're going to see a mix of some general examples, and I'm actually going to pull in some examples from the stuff we worked on.